geometric series is the sum of the terms of a geometric sequence. In applications, it may be necessary to find the sum of the terms of each sequence. For example, a scientist might want to know the total number of insects in 4 generations of the population discussed in example 4. So that would be the partial sum of 4 terms of a geometric sequence. 100 is the first term, times 1.5 is 150, times 1.5 was 225, plus the 338, that was the fourth term we found, and that's 813. If a geometric sequence has first term a sub 1 common ratio r, then the sum s sub n of the first n terms is given by the following formula. A sub 1 times 1 minus r to the n all over 1 minus r. We just got to make sure that r does not equal 1 because that would create a 0 in our denominator. So from the previous problem, that s sub 4, our partial sum, would be 100, that's a sub 1, 1 minus our r, which was 1.5 to the 4th power, divided by 1 minus 1.5. These are best to do in your calculator. So I typed it in, 812.5. Again, that's the 0.5 we had from this last term, which we rounded up, and we'll call it 813. Example 5 and example number 1, we found an employee who had an incredible salary setup. So how much will they have totally earned altogether after 30 days? So using our sum formula for a geometric series, a sub 1, that's going to be this 1 cent. Our ratio will be 2, and n will be 30 for those 30 days. Again, take it to the calculator. 0.01 times 1 minus 2 to the 30th power all over 1 minus 2. And again, if you want to mentally say that's negative 1, you can type it in like that. I'm just mimicking the formula. Well, that comes out to be $10,737,418.23. All right, example number 6, evaluate the following. Okay, now we have a summation symbol. First thing we have to do is find our first term. So we're going to have to take the 1 and substitute it into the I. So that's going to be 3 to the first power. 2 times 3 is 6. That's my first term. We're going 1 to 6, so the sum of 6 terms will equal 1 minus, because we're multiplying by 3 to the power of I. 3 is my common ratio. 3 to the 6th power, that's my n again, over 1 minus 3. Again, go to the calculator, 2,184. Now, in B, we're going to do the same thing, but we have to understand that we're not starting at 1, but we still need the first term. So we're going to put 4 in for I. That's 1/2 to the 4th power, or 1 over 2 to the 4th, which is 1/16. That's the first term. Now here's where it gets tricky. You have to remember, you can't go 10 minus 4 is 6, because we are leaving out the first 3 terms when I is equal to 1, 2, and 3. So it's 10 minus 3. We're finding the sum of 7 terms. So that means my 1/2 will be raised to the 7th power, not the 10 or the 6. Definitely a calculator entry problem here. Because you're using your fraction commands in here, your answer will come back as a fraction, 127 over 1,024. Now, the next thing that we can find is what we call infinite sums. That means we're going to keep adding numbers until it converges to some value. So if we want to consider 2, 1, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, and so on and so on and so forth. If we started adding up the terms, okay, so we know our r is 1/2. And again, second term 1 divided by first term 2, that's your r. So here is the sum of the first term. Sum of 2 terms, 2 plus 1 is 3. Then 2 plus 1 plus, changing this to a decimal, is 0.5. For 4 terms, my 1/4 is now 0.25. That's 3.75, and hopefully you can see now Okay, I get it. You're just adding to the previous term. So 1/8 is 0.125. So I'm just going to take the previous 3.75 instead of rewriting this all the time. Just add it to 0.125, and 3.75 plus that 0.125, 3.875. And then for some of the first 6 terms, we'll do that again. 3.875, now 1/16 is 0.0625, and we have 3.9375. So what I wanted to do is, I'm guessing, it looks like, because now that there's a 0 here, that, okay, this 9 isn't going to change unless I can carry over, but the 6 and the 3 will make that a 9. I'm going to get a lot more zeros where this number's not going to change. So I'm guessing it's a 4. So I went to my calculator and I typed in my formula, 2, that's our first term, times 1 minus our r, 0.5 to the power of x, over 1 minus 0.5. And I went to my table, and so here's the 6th term right there, 3.9375. But if you notice, the 7th term, 8th term, the sum of 9, sum of 10, sum of 11, I'm at 3.9980. So I'm adding always to the end of this, but if I keep going, it appears that we're definitely approaching 4. So this is going to eventually converge to a total of 4. All right, so if n is large enough, then S of n is close to 4 as desired. As mentioned in 8.1, we say that the sequence converges to 4. This is expressed as, okay, here comes your calculus notation again, the limit of S sub n as n approaches infinity or increases without bound is going to equal 4. So since that limit as n approaches infinity of our S sub n is equal to 4, then the sum of the infinite geometric sequence will add up to be 4. Eventually, you are adding so little values, it's going to equal 4. Again, it's like taking a grain of sand and tossing it into the Sahara Desert. You really don't make a difference. It's all there. All right, so if a geometric series has a first term a sub I and a common ratio r, then the sum, S sub n, the partial sum equals a sub 1 times 1 minus r to the nth over 1 minus r, where again, r cannot be equal to 1 for every positive integer n. Now, if r, the absolute value of r, so we're just looking at the positive, it works for negatives too, and I'll show you that, is less than 1, then the limit of your fractional r, somewhere between 0 and 1, raised to the nth power, and as n goes to infinity, that number is approaching 0. We already showed you that. That's like that horizontal asymptote rule. Well, if that r to the n power is going to be going to 0, then 1 minus 0 is 1, and we now have a sub 1 over 1 minus r. So this is the sum of the terms of an infinite geometric sequence. So to show you, here's, I put in y equals 0.1 to the x power, using 0.1 as my r, 0.5, and 0.9. It doesn't matter if you're really close to 0 or really close to 1. As you can see, with 0.1 being closer to 0, it approaches 0 much faster. 0.5 is getting to 0 as well. 0.9 is taking its time, but it's still getting smaller and smaller. It will approach 0. And even if I put negatives on those bases, my signs are alternating, but they're still approaching 0. I'm just bouncing back and forth, if you will, over. If you try to plot this on the x-axis, it's still approaching 0. So you will, anytime you have an infinite series, it's going to be now S sub infinity is equal to a sub 1 over 1 minus r. So if you see a summation symbol with infinity, we want to use this formula. So quick examples here. Evaluate the following: 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81. I can see that the bottom is constantly being multiplied by a 3. So the whole thing is being multiplied by a third, and with a dot, 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 that means we're going to infinity. So first term is 1, your r is 1/3. Again, 1/3 divided by 1, 1/3. So to our formula, first term put in a 1, 1/3 goes in for r, 1 minus 1/3 is 2/3. You don't divide by a fraction, you multiply by its reciprocal. Its sum is 3/2 or 1.5. For b, I see the summation with the infinity symbol. Now, this notation kind of looks like my a sub 1 times an r to the n minus 1 power. It's just that it's I minus 1 because it's its index. So this is definitely a geometric sequence function. So a sub 1 is the -3/4 and the r is a -1/2. So again, we can use our formula here. So -3/4 is a sub 1. 1 minus a -1/2, that's plus plus, so that's 3/2 on the bottom. Again, don't divide by fractions, you multiply by its reciprocal. You can reduce the 3's, 2/4 reduces to a 2 on the bottom. Our sum is -1/2. And that wraps up our 8.3.